Hi, in this lesson I want to go through the ways in which we can date the rocks in the Grand Canyon and how we can apply relative dating techniques to the rocks that we see there. You should have your Grand Canyon handout annotated from the first part of this lesson. Don't be afraid though to add extra detail to it if you need. Okay, let's go. Okay, you've got your block diagram with the different units we can see here on the diagram. Let's start by looking at the Supi Sandstone. I asked what the relative age of the rocks in this canyon is. These rocks, we can tell, have the oldest rocks at the bottom of the canyon, near where the river is, and the younger rocks then will be at the top of the canyon. This is an application of the law of superposition. As long as the beds are the right way up, they haven't been overturned, the oldest is going to be at the bottom of the sequence, the youngest is at the top. The rocks in the Grand Canyon are all the correct way up. So we can apply superposition to this side canyon, but also to the whole canyon, with the oldest rocks being right down by the river at the bottom of the canyon, and the youngest rocks are going to be the ones you're sitting on at the rim looking down on this. If we look at the fossil content, this confirms this principle of superposition. We can see down in the Bright Angel Shale there, we find trilobites. Now trilobites we know were most common during the Cambrian and early Ordovician, and they'd become extinct by the end of the Permian, although to be honest they'd pretty much disappeared by the time we're getting into the Carboniferous. So we know that the Bright Angel Shale is far more likely to be lower Paleozoic. Now the Kaibab Formation near the top of this is Permian in age. What we see here is a cephalopod. Now a shell cephalopod didn't evolve until later. This one's actually a ceratite. More about that in a later lesson. But the times we find these fossils are different, and we know that the cephalopod came after the trilobite. So we've got a confirmation from the fossils that superposition works here in the canyon, and also we can actually, if we identify these down to a species level, we can actually come up with an exact date using these fossil content of these beds. Now, when we go down to the bottom of the canyon, and we look at the boundary between the tapetes and the Vishnu schist, we can see an interesting feature within it. We can see these lumps of quartz. These lumps of quartz have been eroded from the Vishnu schist and then deposited in the tapetes. These are what we call included fragments. And by the principle of included fragments, we can tell that the tapetes must be younger than the Vishnu schist because it's got bits of the Vishnu schist in the tapetes. They had to exist before the tapetes was laid down. If we look at the Zoroaster and the Vishnu schist, Zoroaster is a granite, Vishnu schist is a metamorphic rock, we can see that the Zoroaster has been injected into the Vishnu schist. This is a cross-cutting relationship. It tells us that the Zoroaster granite must be younger than the Vishnu schist, because this granite has been intruded or injected into the pre-existing Vishnu schist. There's an even more striking cross-cutting relationship here in the Shinumu sandstone. Here we've got a dike, looks sort of mafic in composition, cutting very distinctly and discordantly through the bedding in the Shinumu sandstone. It tells us that this dike must be younger than the Shinumu sandstone. Must be. Because the Shinumu sandstone had to be there for that dike to be injected into it. If we went and found some baked and chill margins in this, we'd have that confirmed for us as well. The tapetes and the docks formation, this is a little more subtle. The docks formation underneath, you can see, is gently inclined down to the right. It's dipping to the right. The tapete sitting on top, though, is pretty much horizontal. So there's a difference in the angle of dip between these two units of rock. This is a feature we call an unconformity. It tells us that there's been a gap in time, because the docks formation here has been deposited, been laid down, it's become a rock. It's then been tilted to this angle, eroded off before the tapetes was deposited on top. So the tapetes there, you'll notice, cuts across the docks formation. So we've got a cross-cutting relationship. Crucially, we've got an unconformity. It tells us we've got different cycles of deposition, and that the tapetes here on top must be younger than the ones below. Now, this is a type of unconformity we call an angular unconformity, because the angle of dip is different. If we look down at the bottom here, again between the tapetes and the Vishnu schist, again you can sort of see an angular difference. The structures in the Vishnu schist at the bottom are almost vertical. The layers in the tapetes there are almost horizontal. More importantly, though, there must be a massive gap in time between these two units of rock because of the way they form. Vishnu schist is a regional metamorphic rock. It's been formed at depth in the crust, maybe 15 kilometres down. The tapetes, though, is a sedimentary rock. That was formed at the surface. Those two rocks could not have been together when the Vishnu schist was metamorphosed. If it was, the tapetes would also be metamorphosed. So that Vishnu schist must be much, much older than the tapetes. Because we have such different rocks here, there must be a massive gap in time. And we call this a heterolithic unconformity. Heterolithic means different rock. Hetero in Greek is different, lithic is rock. And it means that we have two rocks here that are together that could not have formed together. They must have formed because of the different processes that have happened at very different times. We can see within this that there are several different unconformities within this particular, or within the canyon. Some of them are really obvious, like the angular unconformity there we see near the base, or the heterolithic unconformity we've just been talking about with the Vishnu schist and the tapetes. But there are also these what we call disconformities, where actually you've got to really look carefully to find the gaps. For example, between the Cambrian and Devonian, that means the Ordovician and Silurian periods are completely missing at that point. But the rocks seem to just continue. Same with the big disconformity there in the middle between the Mississippian and Pennsylvanian. It's not immediately obvious. Certainly not in the canyon. The Cadenus basalt lavas have been dated there to just 1.1 billion years. That, where we can put an age on a rock, and that is something for another lesson, we can then date the rocks around it relative to that. As we said in part one, by applying these sequences not just in the Grand Canyon but in these other areas, Zion Canyon, Bryce Canyon, in sort of the Colorado Plateau, this area sort of in Utah, it enables us to come up with this huge sequence of geological time. This incredible record going from the lower Precambrian right the way through almost to the present day. So, application of these principles, which we can apply in so many different places within geology, not just the spectacular geology of the Grand Canyon, allows us to establish the relative age of rocks, and with it, what we call a geological history, a story of the events that have occurred to create the geologies that we see. Now we need to try and apply this a little bit more, perhaps to a location closer to home, but we'll do that in another lesson. I'll see you then.